In today's video, we undervolt and overclock the AMD Ryzen 7 9800X3D processor all the way up to 5750 MHz using the Asus ROG Crosshair X870E Hero motherboard and some AIO water cooling. I achieved this primarily by relying on asynchronous eCLK to stretch the CPU's VF curve beyond the Precision Boost maximum allowed frequency. And I also need to use Curve Shaper to make the whole system stable. In this video, I break down the Ryzen 7 9800X3D tuning process into 4 unique overclocking strategies for beginner and advanced overclockers. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that I'll be using in this guide. The AMD Ryzen 7 9800X3D is part of AMD's Zen 5 based Ryzen 9000 desktop processor product line, codenamed Granite Ridge. The Granite Ridge processors were introduced on June 2nd, 2024 during Computex. The Ryzen 7 9800X3D succeeds the 8-core Zen 4 Ryzen 7 7800X3D, which we overclocked in SkatterBencher number 60. It has a base clock of 4.7 GHz and a listed boost frequency of up to 5.2 GHz. Just like its predecessor, its TDP is capped at 120 watts. The system we're overclocking today consists of the following hardware. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before starting overclocking, of course, we have to check the system performance at stock. The default Precision Boost 2 parameters for the Ryzen 7 9800X3D are as follows. Here's the benchmark performance at stock. Here are the 3DMark CPU profile scores at stock. Here's the OCCT benchmark score at stock. Here are the AIDA64 memory benchmark scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4880 MHz with 1.104 volts. The average CPU temperature is 83.8 degrees Celsius. The average CPU package power is 141.3 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5181 MHz with 1.205 volts. The average CPU temperature is 87 degrees Celsius. The average CPU package power is 149 watts. Of course, we can increase the maximum power consumption limit by enabling Precision Boost Overdrive, and that's exactly what we'll do in our first overclocking strategy. However, before that, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button will reset all your BIOS settings to default, which is very helpful if you want to start your BIOS configuration from scratch. In our first overclocking strategy, we simply take advantage of enabling Precision Boost Overdrive and AMD EXPO. With the launch of Zen 5, AMD introduced an improved version of their Precision Boost Overdrive 2 overclockers toolkit. Basically, this toolkit allows us to manually fine-tune some of the parameters that are governing the Precision Boost 2 boosting algorithm. The Precision Boost Overdrive 2 toolkit for Zen 5 Ryzen processors includes the overclocking knobs from Zen Plus, PPT, TDC and EDC, Zen 2, Boost Override and Scalar, Zen 3, Curve Optimizer, and the newly announced Curve Shaper for Zen 5. There are essentially 3 levels of Precision Boost Overdrive. By enabling Precision Boost Overdrive, we rely on the motherboard pre-programmed PBO parameters. We find that the following values have changed. Increasing the PPT and to a lesser extent the TDC and EDC limit will help unleash the frequency in multi-threaded workloads previously limited by the PPT. EXPO stands for AMD Extended Profiles for Overclocking. It's an AMD technology that enables ubiquitous memory overclocking for AMD platforms supporting DDR5 memory. EXPO allows memory vendors such as G.Skill and XPG to program higher performance settings onto the memory sticks. If the motherboard supports EXPO, you can enable higher performance with a single BIOS setting, so it saves you from lots of manual configuration. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 1. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to enabled, then save and exit the BIOS. The boost frequency at one active thread is about 5225 MHz, and the average boost frequency gradually trails off to 5185 MHz when all cores are active. All cores can boost to over 5.25 GHz in single-threaded workloads. We reran the benchmarks and checked the performance increase compared to the default operation. Unlike the first single CCD Ryzen 9000 processors, the Ryzen 7 9800X3D isn't limited by the power limits, so enabling PBO doesn't have that much of a performance impact. However, the improved memory performance by enabling EXPO does translate into some small, single-digit performance gains across the board. The geomean performance improvement is plus 2.40%, and we get a maximum improvement of plus 13.45% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4857 MHz with 1.105 volts. The average CPU temperature is 83.5 degrees Celsius. The average CPU package power is 151.6 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5163 MHz with 1.207 volts. The average CPU temperature is 87.7 degrees Celsius. The average CPU package power is 168.4 watts. In our second overclocking strategy, we tune the CPU's Precision Boost 2 boosting algorithm by using some of the tools available in the Precision Boost Overdrive 2 toolkit. Fused maximum frequency, or Fmax, is one of the Precision Boost infrastructure limiters managing the CPU performance. Essentially, Fmax determines what's the maximum allowed operating frequency for each of the 8 cores in our Ryzen 7 9800X3D. Boost Clock Override, or Fmax Override, is one of the tools available in the PBO2 Overclockers toolkit. It allows the user to override the arbitrary clock frequency limit between -1000 and +200 MHz in steps of 25 MHz. The programmed limit for the Ryzen 7 9800X3D is 5250 MHz. So, with an Fmax of +200 MHz, we have a new maximum frequency of 5450 MHz. It's important to note that the Fmax override only adjusts the upper ceiling of the frequency and doesn't act as a frequency offset. Ultimately, it's the Precision Boost 2 boosting algorithm that still determines the actual operating frequency. Scalar is a tool that allows us to override the warranted silicon stress level, or FIT. You can adjust the maximum allowed FIT level to 10 times higher than the factory fused limit. While the tool offers precise granularity, typically you'll find the available options to range between 1x and 10x in steps of 1 multiple. The effect of increasing the scalar is that the CPU will pursue higher voltages more aggressively, and that's important to enable higher frequencies. Now, the relevance of this scalar tool depends architecture to architecture. And it seems that Zen 5 kind of benefits from scalar because it's pretty voltage limited. The voltage limit is 1.45 volt, though we only see slight excursions above 1.4 volt in really light single-threaded workloads. When all 8 cores are active, the maximum voltage is 1.35 volts. It's difficult to observe the limit with this particular Ryzen 7 9800X3D because the default curve only goes up to 1.18 volt for 5.25 GHz. However, we can observe it more easily by applying a positive curve optimizer. With a 10x scalar, we find that in an all-core workload, the maximum voltage increases from 1.35 to 1.37 volt. That's not a big increase, but in voltage-constrained scenarios, every little bit helps. Curve Optimizer has been one of the most important tools for overclocking AMD Ryzen CPUs. It is most commonly known for its undervolting capabilities, but for AMD Ryzen CPUs, it kind of also works as an overclocking tool. To explain how it works, let's start with the basics, the voltage frequency curve. Simply put, a voltage frequency curve describes the relationship between an operating frequency and the voltage required to operate at that frequency. Every modern SoC has a factory-fused voltage frequency curve and uses this to dynamically adjust the power consumption depending on the workload needs. Here's the default voltage frequency curve of my Ryzen 7 9800X3D processor. This curve represents the average curve of the 8 cores inside the CTD because actually every of the 8 cores has its own curve. We can immediately make a simple and redundant observation. The higher the frequency, the more voltage is required. For example, we only need 1.01 volt for a frequency of 4.5 GHz. However, we need over 1.13 volt for 5.1 GHz. Although it's not obvious from the VF curve, the maximum allowed voltage is 1.35 volt when all cores are active. The Precision Boost 2 algorithm utilizes the VF curve to find what's the maximum possible frequency at 1.35 volt. With the default curve, that's 5225 MHz at 1.18 volt. As I explained just a minute ago, we can use the Fmax boost override tool to increase the Fmax by another 200 MHz. Now, the Precision Boost algorithm pushes the CPU up to 5425 MHz at 1.328 volt, still below the 1.35 volt threshold. If we set a negative curve optimizer, we can shift the entire voltage frequency curve along the voltage axis. And suddenly we need a lot less of voltage for every operating frequency. For example, for 5.1 GHz we needed about 1.13 volt by default, but with a -40 curve optimizer, now we only need 0.998 volts. Curve optimizer is a very powerful tuning tool. It's simple, but not simplistic. And the more you dig into how it works and how you can apply it to your system, the more complex it gets. Typically, we use curve optimizer by setting a negative value, and that helps in two ways. First, undervolting lowers the operating voltage, temperature, and power consumption. Second, as a consequence, the Precision Boost 2 algorithm can leverage the additional headroom to boost to higher frequencies. So you tend to get lower temperatures and higher performance. It's a win-win. However, there are a couple of caveats when it comes to using curve optimizer. Curve optimizer impacts the entire voltage frequency curve, so it affects stability across the entire range of operating frequencies, from 600 to 6000 MHz. The same curve optimizer value also impacts differently across the curve. If you're lucky, your CPU's undervolt margin matches how curve optimizer offsets the voltage. In that case, you'll quite easily get some performance gains. But if the margin of your CPU is somewhere less than in other places, then your curve optimization route or journey can be quite tricky. Curve optimizer is available on a per CPU, per CCD, and per core basis. The manual tuning process for curve optimizer can become quite convoluted because it spans a very wide range of workloads, from light single-threaded workloads all the way to heavy all-core workloads. I want to emphasize this point and refer to my Ryzen 9 9950X overclocking guide, where I demonstrated that the VF curve changes depending on the workload. With a dynamic voltage frequency scaling technology like Precision Boost 2, it's important to check stability across the range of workloads, because sometimes it can happen that your system is fully stable in your all-core AVX workload and then blue screens when you're playing a game. I identified 4 typical workloads that tend to show early signs of instability. So when I increase the negative curve optimizer setting in steps of 5 points, I quickly check stability with each of these workloads. Once I find an instability, I back off on the curve optimizer and check the stability across the entire benchmark suite. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 1. Switch to the Advanced menu. Enter the AMD Overclocking submenu and click Accept. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set Precision Boost Overdrive Scalar control to Manual. Set Precision Boost Overdrive Scalar to 10x. Set CPU boost clock override to enabled positive. Set max CPU boost clock override to 200. Enter the curve optimizer submenu. Set curve optimizer to all cores. Set all core curve optimizer sign to negative. Set all core curve optimizer magnitude to 40. Then save and exit the BIOS. The boost frequency at one active thread is about 5425 MHz, which is maintained even when all cores are active. All 8 cores can boost to over 5.45 GHz effective clock in single-threaded workloads. We reran the benchmarks and checked the performance increase compared to the default operation. Combining the impact of extending the maximum frequency by 200 MHz with quite a dramatic undervolt showed a pretty substantial impact on the boost curve. However, even though we can definitely see the performance improve, we're not seeing spectacular gains. The geomean performance improvement is plus 4.84%, and we get a maximum improvement of plus 15.45% in AI benchmark. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 5224 MHz with 1.073 volts. The average CPU temperature is 82.2 degrees Celsius. The average CPU package power is 150.4 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5421 MHz with 1.182 volts. The average CPU temperature is 84.6 degrees Celsius. The average CPU package power is 157 watts. In our third overclocking strategy, we have a look at optimizing the memory subsystem performance. On AMD Granite-rich processors, there are 3 important parts of the memory subsystem: the Infinity Fabric, the memory controller, and the system memory. They're more commonly referred to as Fclock, uClock, and incl. First generation Ryzen overclockers know that these parts used to be tightly coupled together, but on modern Ryzen processors like the Ryzen 7 9800X3D, we can tune them independently. There were 3 things I wanted to address with the memory subsystem performance optimization. I want to run the Fclock as high as possible, I want to run the uClock and incl in sync, and I want to tighten up the memory timings. The fabric frequency, or Fclock, is generated by the SoC PLL derived from a 100 MHz reference clock input. The reference clock input is multiplied by the Fclock ratio, which you can configure in the BIOS. The standard operating frequency of the Infinity Fabric with a 2x16GB memory kit is 1800 MHz, but on many boards you'll find that it runs 2100 MHz when Precision Boost Overdrive is enabled. That said, it doesn't seem there's much overclocking headroom beyond 2100 MHz. I managed to set it to 2200 MHz for this overclocking strategy, however anything higher than that couldn't boot reliably, not even with voltage adjustments. Speaking of the voltage, the Infinity Fabric voltage is provided by the VDD-G voltage supply, derived via an integrated voltage regulator from the VDD-CR miscellaneous voltage rail. There's a total of 2 VDD-G voltage rails available for manual adjustment. AMD Granite Ridge has 2 DDR5 Unified Memory Controllers, or UMC in short, and each provides 2 32-bit memory channels. The memory controllers are located in the I/O die and are identical to the memory controllers on Ryzen 7000 Raphael processors. The Unified Memory Controller Frequency, or uClock, is derived from the UMC clock, one of the SoC PLLs. The memory controller frequency is tied directly to the system memory frequency. It can run either at the same or half its frequency. At default, the memory controller runs at the same frequency as the system memory at 2400 MHz. However, we find that when we enable EXPO, the motherboard auto rules will drop the memory controller frequency to half that of the memory frequency. We can easily force the memory controller to run at the same frequency as the system memory by setting uClock div1 mode to uClock equals memclock. The VDD-CR SoC voltage rail provides the external power for multiple internal voltage regulators on the SoC for the various IP blocks, including the memory controller. The VDD-IO memory voltage rail is related as it provides the external power for the VDD-P DDR5 bus signaling. The last piece of optimizing the memory subsystem is optimizing the system memory timings. For this, I rely in part on ASUS's memory presets and in part on the knowledge that I've gained in previous SkatterBencher guides. ASUS memory presets is an ASUS overclocking technology that provides a selection of memory tuning presets for specific memory ICs. The presets will adjust the memory timings and voltages. The ROG Crosshair X870E Hero motherboard sports 14 memory profiles for a variety of memory ICs and configurations. Since we are interested in simply adjusting the memory timings, we can try the Hynix 6400 MHz 1.4 volt 2x16GB single rank preset. Note that I stick with the EXPO primary timings and only leverage the memory preset for secondary and tertiary subtimings. Similar to the Ryzen 5 9600X, which I overclocked in SkatterBencher number 79, I had to lower the memory frequency from the EXPO rated DDR5 6400 to DDR5 6200 to maintain stability with the tighter memory timings. After the tuning of the memory subsystem, our ADA 64 performance improved quite significantly. We got about plus 25% extra performance by enabling EXPO and added another 12 to 15% on top of that by tuning the memory timings. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 1. Set memory frequency to DDR5 6200. Enter the DRAM timing control submenu. Enter the memory presets submenu. Select Load Hynix 6400 MHz 1.4 volt 2x16GB single rank and click OK. Leave the memory presets submenu. Leave the DRAM timing control submenu. Switch to the advanced menu. Enter the AMD overclocking submenu and click Accept. Enter the DDR and Infinity Fabric Frequencies timing submenu. Enter the Infinity Fabric Frequency and Dividers submenu. Set Infinity Fabric Frequency and Dividers to 2200 MHz. Set uClock Div1 mode to uClock equals memclock. Leave the Infinity Fabric Frequency and Dividers submenu. Leave the DDR and Infinity Fabric Frequency timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set Precision Boost Overdrive Scalar Control to Manual. Set Precision Boost Overdrive Scalar to 10x. Set CPU Boost Clock Override to Enabled Positive. Set Max CPU Boost Clock Override to 200. Enter the Curve Optimizer submenu. Set Curve Optimizer to All Cores. Set All Core Curve Optimizer sign to negative. Set All Core Curve Optimizer magnitude to 40. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Tuning the memory subsystem has a surprisingly large impact on the benchmark performance. The standout performance improvement is PY Prime, where we see a maximum improvement of plus 38.17% over stock, but that's very much a memory benchmark. However, we also see a performance uplift of 5 to 10 percentage points in other multi-threaded benchmarks such as Geekbench and AI Benchmark. The geomean performance improvement over stock is plus 6.44%. In the fourth and final overclocking strategy, we leverage eClock mode. eClock stands for external clock, and it is exactly like the term suggests. We use an external clock generator. Using the external clock generator, we can warp the Precision Boost voltage frequency curve to achieve higher frequencies than programmed into the CPU. The standard Granite Ridge platform has a 48 MHz crystal input to the integrated CGPLL clock generator. The CGPLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. Granite Ridge supports up to 2 external clock modes. They're called eClock 0 mode and eClock 1 mode. In eClock 0 mode, an external 100 MHz reference clock is used for both the CPU and SoC PLLs. In other words, it's a reference clock that affects the CPU core clocks as well as the PCI, SATA, and SoC clocks. In eClock 1 mode, there are 2 distinct external 100 MHz reference clocks. One clock provides the 100 MHz input for the CPU PLL, and another provides the 100 MHz reference clock for the SoC PLLs. The overclocking strategy with eClock is the polar opposite of what we're used to when we're overclocking AMD Ryzen CPUs. If you remember, in OC strategy number 2, we approached it in the typical way. We use curve optimizer to undervolt the CPU. And by undervolting, we get a little bit more frequency headroom, and also we get lower voltages for a given frequency. When we use eCLK, we still rely on the same factory fused voltage frequency curve. However, we stretch the frequency out. So for a given voltage, we actually increase the frequency. Let me explain with an example. Here you can see two VF curves of the Ryzen 7 9800X3D, the default curve and the one from OC strategy number 2 with the -40 curve optimizer. We can see the law of diminishing marginal returns. The higher the frequency, the less additional frequency with every step of additional voltage. For example, on the default curve, increasing the voltage from 1 volt to 1.05 volt gives an extra 300 MHz, but increasing from 1.1 volt to 1.15 volt only gives an extra 175 MHz. The law of diminishing returns also applies to our undervolt. With a -40 curve optimizer, we get an extra 675 MHz at 1 volt, but only 425 MHz at 1.1 volt. If we were to increase the eCLK by 5.5%, setting it to 105.5 MHz, then the resulting curve would look as follows. We can make 3 key observations. First, the frequency increases by 200 to 250 MHz across the entire curve and doesn't show any diminishing returns. 2. While the voltage for a given frequency is lower than the default curve, it is higher than our curve optimized curve. For example, for 5 GHz we need 1.107 volt by default, about 1.056 volt when using 105.5 MHz eCLK, but only 0.978 volt when curve optimized. 3. The curve now extends well beyond the 5450 MHz Fmax, for which there's no guaranteed operating voltage defined by the factory fused VF curve, so we don't know if it's stable over there. Before Ryzen 9000, we could only rely on the curve optimizer tool to gain stability. Basically, we would use a positive curve optimizer to gain stability at the upper end of the curve, so to support the higher frequencies, but we would have to sacrifice some frequencies lower down the curve because we increased the voltage for certain frequencies, basically. With Ryzen 9000, fortunately, we have a new tool, Curve Shaper. Curve Shaper is the newly announced CPU tuning tool included with the Precision Boost Overdrive 2 toolkit. It was announced together with the Zen 5 desktop CPUs, and I've already had an in-depth look at the tool in several other videos on this channel. In theory, it seems Curve Shaper is pretty straightforward. You get 15 additional tunable points across the VF curve. But the devil is in the details because AMD's Precision Boost 2 technology doesn't really work with VF points. So instead of getting a list of specific tunable VF points, we get 5 frequency regions and 3 temperatures. The regions have a bit of a vague terminology and are not clearly defined. I will get back to that in a minute. The temperature points are more straightforward as they're defined as -5, 50 and 90 degrees Celsius. The idea of Curve Shaper is that you can adjust the voltage frequency curve in different parts along that curve. So for example, you could say that you only want to undervolt for high frequencies between 50 and 90 degrees Celsius. That could be a use case, for example, for a gaming situation. We want to use Curve Shaper for 2 reasons. We want to use positive values to improve stability at the upper end of the curve, and 2, we want to claw back the undervolting potential at the lower end of the voltage frequency curve. For the first objective, we can use positive Curve Shaper values for high and maximum frequency regions. For the second objective, we can use negative Curve Shaper values for min, low, and medium frequency regions. Let's get a bit more practical with the process. Similar to Curve Optimizer, the tuning process with eCLK and Curve Shaper can become quite convoluted because we're still talking about that wide range of workloads, from light single-threaded workloads all the way to heavy all-core workloads. My first goal was to find the maximum stable frequency at the upper end of the curve. Here I found that the first workload to show signs of instability was yCruncher BKT. This is a light all-core workload that boosts the frequency very high. I found it tricky to get stability over 5.5 GHz even with significantly higher voltages. Here's the resulting curve with an E-clock frequency of 105.5 MHz and a high maximum frequency curve shaper of +15. You can see the curve starts to diverge from the base E-clock curve at about 5.2 GHz. The next objective is clawing back the undervolting potential. Here I found that the yCruncher 5B benchmark gives the first signs of instability. That's a pretty heavy dynamic all-core AVX workload. The undervolting headroom was much more satisfactory than the overclocking headroom, as I could set a maximum negative curve shaper for min, low and medium frequency. Here's the resulting curve with an E-clock frequency of 105.5 MHz, a high max frequency curve shaper of +15, and a min, low, medium frequency curve shaper of -30. You can see that we effectively clawed back all the undervolting headroom up to about 5.2 GHz. Curve shaper is a very powerful tuning tool, and this example perfectly captures its core strength, adjusting the under and overvolt at different parts of the curve, which maximizes the frequency in light and heavy workloads. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 1. Set eClock mode to asynchronous mode. Set BCLK2 frequency to 105.50. Set memory frequency to DDR5 6200. Enter the DRAM timing control submenu. Enter the memory presets submenu. Select Load Hynix 6400 MHz 1.4 volt 2x16 GB single rank and click OK. Leave the memory presets submenu. Leave the DRAM timing control submenu. Switch to the advanced menu. Enter the AMD overclocking submenu and click Accept. Enter the DDR and Infinity Fabric frequency timings submenu. Enter the Infinity Fabric frequency and dividers submenu. Set Infinity Fabric frequency and dividers to 2200 MHz. Set uClock div1 mode to uClock equals memclock. Leave the Infinity Fabric frequency and dividers submenu. Leave the DDR and Infinity Fabric frequency timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set Precision Boost Overdrive Scalar control to Manual. Set Precision Boost Overdrive Scalar to 10x. Set CPU Boost Clock Override to Enabled Positive. Set Max CPU Boost Clock Override to 200. Enter the Curve Shaper submenu. For all parameters, set Low, Medium and High Temperature to Enable. For min, low and medium frequency, set Sign to Negative and Magnitude to 30. For high and maximum frequency, set Sign to Positive and Magnitude to 15. Then save and exit the BIOS. The boost frequency at one active thread is about 5636 MHz, and the average boost frequency gradually trails off to 5398 MHz when all cores are active. All 8 cores can boost to well beyond 5.7 GHz in single-threaded workloads. We reran the benchmarks and checked the performance increase compared to the default operation. Overclocking with asynchronous eClock is somewhat of an academic exercise, because its main purpose is to overcome the Precision Boost Fmax limit in 1T scenarios. We can see there's a small performance improvement in the single-threaded benchmark applications, but for the most part, the performance is identical to when we just use Curve Optimizer. The geomean performance improvement is plus 7.16%, and we get a maximum improvement of plus 39.27% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 5248 MHz with 1.093 volts. The average CPU temperature is 86 degrees Celsius. The average CPU package power is 158 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5393 MHz with 1.206 volts. The average CPU temperature is 89.2 degrees Celsius. The average CPU package power is 166.5 watts. Alright, let's wrap this up. The AMD Ryzen 7 9800X3D represents AMD's best so far for Zen 5 on the desktop. And for the very first time, there's official support for overclocking the X3D CPUs. Even though we did overclock the 5800 X3D and the 7800 X3D in previous videos on this channel. The overclocking process with the X3D CPUs is identical to the other single CCD processors. However, I was quite surprised by how much overclocking headroom there really was. I could run OCCT AVX all-core at 5.2 GHz with 1.1 volt and even the SSE workload with 5.4 GHz at 1.2 volts. So that is pretty good. Other than that, I don't really have anything to comment about X3D overclocking. It's pretty much like you overclock any other AMD Ryzen CPU. It's interesting that we could use asynchronous eCLK again to go past the Precision Boost limit, and that even got me all the way up to 5.9 GHz. Not quite 6, but maybe we'll get there at some point. Anyway, that's it for this video. I want to thank you for watching and the patrons for the support. If you have any questions or comments, feel free to drop them in the comment section below. Of course, I will also publish a written version of this video on my blog, so have a look there if you want to read through my BIOS settings or have a look at the benchmark results. And that's it. See you next time.